On real bundle gerbes.
Thanks, Paul. And thank you to the organisers for inviting me here to this. Maybe I should, of course, remember to put a map on my talks, just in case everybody knows where Adelaide is. I know it's such a large place, but if that's sort of, not to forget my wife, I should put Tasmania on there. There's that little bit that sticks up here, so Adelaide's about there, Melbourne's there. Yeah. Sydney's the one with the Opera House. That's there. Okay, so there's always a problem in fitting your talk, making your talk match the conference, but I realised there's an easy way to do that, which is to change the conference title. So I think my talk's in sort of higher geometry and somewhat in higher twists, less in temporally lead algebras or Calabi-Yau algebras. So this is this on? Yes. All right. This is part of a larger project with some colleagues, Pedram Hekmati, who's now in Auckland, Richard Szabo, who's at Heriot-Watt, and Raymond, Vozzo, who's also in Adelaide, and this paper. And so part of this paper was real bundle gerbes. There are some other things, orientifolds and twisted KR homology. So the twisted KR homology, of course, relates back to the sort of K homology that was talked about earlier in the week. But what I'm going to talk about are the real bundle gerbes. So I'm just wiping out the things I don't want to talk about. So in summary, what I'll do is say something about real spaces, what a real space is, and I'll say something about real, and also we need to think about equivariant bundles, something about a particular cohomology theory that comes from Grothendieck. Then I'll have to say something about bundle gerbes so you know what they are, and then I'll say what a real bundle gerbe is, and then there are sort of two approaches to real bundle gerbes. I mean, basically because bundle gerbes are rather categorical and there are different kinds of morphisms you can have between them. And so when you want to have an action on them, you can decide whether you sort of have a strong action or a weak action. And so the strong version is the kind of real bundle gerbes. The weak action is the what are called Yandel gerbes. And then I'll finish up with a calculation. So I guess I'm interested really in trying to calculate real bundle gerbes, you know, concretely, examples of such, and trying to take examples of bundle gerbes and work out when they are real. So let's go back, and so I should also say, I guess, that one of the reasons I'm going to dwell a bit on equivariant bundles is not just because they're kind of model for what a bundle gerbe looks like. There's a kind of hierarchy of objects. If you look at U1 bundles and you ask yourself what are the automorphisms, well, they're functions into U1, they're gauge transformations, in other words. If you look at bundle gerbes and you ask yourself what are the sort of, well, one way of thinking about the morphisms is the morphisms differ by U1 bundles. So there's a sort of hierarchy of these things that build up. And so you really need to know the things lower down in the hierarchy and how they behave to be able to understand the higher things. All right, so real space, this is a real space in the kind of sense of this paper of Atiyah's that people might know. There's a paper called K-theory in reality where he develops what he calls KR theory. So it's just a pair consisting of a manifold and an involution, smooth involution. And so we call the smooth involution a real structure and the pair a real space, or I guess it could be called a real manifold. So notice that it's really exactly the same thing as a Z2 action, right? That tau, the involution tau, is just giving you the action of the non-trivial element in Z2.
To be very clear, M is a real manifold.
Yes, sorry. M is a real manifold. You notice there's a use of capital R here and there, so I'll try and use lowercase r when I really mean real, as it were. So what we're interested in doing is taking a real space and having some kind of object living over it, like a line bundle or a vector bundle. Not so much that case. That's what Atiyah was interested in, or a bundle gerbe. And we want to try and lift this action. So let's do a really simple example because it gives you an idea of sort of two different things which are important in this, which is we could take functions, right? So don't even take line bundles, take functions from manifold into U1. They're a really simple sort of object. And let's define, sorry, that was meant to be me pressing the laser pointer. Right. define tau of a function by taking your function and giving a new function whose value at m is the old function evaluated at tau of m, that's involution, and then you conjugate. That's kind of. You'll notice that I'm using tau here and tau here. I'm going to use tau everywhere. I guess if I want to conjugate linear involution, I should call it star, but I won't. So notice that tau squared is f. You do this twice, you get back to f. So we're going to call f real if tau of f is equal to f, or in other words, if f of x is the conjugate of f of tau of x. And so there are two examples in this kind of story that are worth sort of bearing in the back of your mind. One is the really simple case where tau is the identity. Right? So then, if tau is the identity, this says that f of x is real, right? So f of x is f bar is the conjugate of f of x. So f really is a real function. And so as I've chosen to have them in U1, of course, that's not very interesting. It's Z2 value. The other thing you could do is to take a manifold X and make two copies of it, so disconnected. Right, so I could have X and X again, so label this one by 0, that by 1. Write down the obvious involution. It sends a point in one sheet to the same point on the other sheet. And then if you go away and you think about what a real function is, it's going to be a pair of functions like f naught, or any function will be a pair of functions, one on each sheet into U1, and it will be real, will mean that f naught is just the conjugate of f1. So in some sense, you don't need to know about both these things, right? If you want to study real functions in this example, then all you need to know about is f naught, say, or f1, depending on which one you prefer. The other one just comes along for the line. It's the conjugate of the other function you're thinking about. So if you want, so real functions on this particular m are just functions on x. And so this was pointed out in Atiyah's paper because this, in his setup, this shows that the KR theory, the real K theory he invented, sort of includes both the KO case, which is like this Z2 example, and it includes ordinary K theory. You can always reduce to the ordinary case by doubling up your manifold. Right, so there's sort of two, in some sense, two extreme examples. So I wanted to just say something briefly. This isn't really so necessary for this talk, but it's kind of interesting. So you could ask yourself, if you've got a space, when has it got a smooth involution? And so you want to decide what you mean by two smooth involutions being the same. And the right thing to do is to say they're equivalent if you can get one from the other by conjugating by diffeomorphism. Right. And so then there are various results that seem to have been proved that there doesn't seem to be sort of much of a general theory. So if we take something simple like the two-sphere, it turns out that every real structure can be conjugated until it's actually just given by the action of a rotation, something from O3. Right, and so you get that on the two-sphere there are essentially four inequivalent structures. You could take the identity map, you could take the antipodal map, or you could take the map that rotates you around some axis by pi, or you could take the map that reflects you in the equator. Right, that's a good one. It brings Australia up to the top of the world where it should be. Right, and so everything else is conjugate to one of those. And so the way this theory, as far as I understand, looking at the papers goes, is you think about the fixed points, right? So this equivalence is going to map the fixed points of tau to the fixed points of tau prime with rho or rho inverse, so diffeomorphically. And so, of course, the identity map, the whole two-sphere of fixed points. The antipodal map, there are no fixed points. The rotation has the top and bottom as fixed points, and the other one has the equator as a fixed point, and that's the only possibilities. That's how you help to classify these things. Right, and so then you can go on and you can try and do other things. So S1 cross S1 apparently has 5 classes of real structures, and S1 cross S2 has 13 classes of real structures. So I leave you to contemplate why this is true. I have no idea. And in fact, I tell a lie. That last paper was for PL manifolds, so it's got replace the word smooth with PL is what the real theorem is. All right, so sorry, I picked up a cold the other day. Either spending 22 hours in a small metal tube with 400 people, probably that. All right, so we take a step up from functions to bundles, right? So a U1 bundle is called a real bundle if you can get a conjugate involution, so map tau from the bundle to the bundle, preserving fibres. So it's essentially a bundle map, except that it's conjugate linear, right? So it's really a map from P to the conjugate bundle, so from P to the bundle usually you call P star, the dual bundle. Right, so I'm going to always just sort of wander between U1 bundles, sort of principal bundles, and Hermitian line bundles, which of course are equivalent objects. Right, so I want the square one. So it's not quite the same as having a Z2 action, right? A Z2 action, I'd want bundle morphisms here, not sort of anti-linear but bundle morphisms. But we'll need that as well in a minute. Right, so the real structure is an isomorphism from the pullback of P to the conjugate bundle. Right, so that gives you some topological problem. If you're going to have a real structure at all, those bundles had better be isomorphic. If they're not isomorphic, you don't have a real structure. However, if they are isomorphic, you still might not have a real structure because there's this additional condition that this tau should be an involution. All right, and so then there's the other thing you could write down, the obvious definition of an Z2 equivariant bundle. It's exactly the same, but this is, you don't want this to be a Z bar. You want this just to be a bundle isomorphism. So it's a lift of the Z2 action on the real space to P. And likewise, there's this topological condition, a necessary but not sufficient condition for the existence of a lift of the action, is that this had better be true. Right, so I'm interested in trying to work out how many real structures there might be, modulo sort of your obvious isomorphisms. And so, if you've got your bundle, so your real structure is going to do something like this, but then you might have some isomorphism here and here and a different. And so in a situation like this, I want to regard this real structure as the same as that one. Right? Because all I've done is applied an isomorphism to the bundle and sort of produced a new T dashed. And so this will be given by some function, right? So isomorphisms of U1 bundles are just multiplication by some function. And some function over here. And so you can just sort of go away and try and calculate things. So this is not hard to do. So, and also if, right, so tau is a map from Px to P tau x, tau dashed will be a map from Px to P tau dash. So tau dashed will really be some function times tau. Right, so it's all just functions. Okay, so, right, so it's a hat. Okay, tau hat is tau dash. So tau hat will be some multiple of tau. That's the only other way. That's the only way you can get a real structure. We'll want it to square to 1, and so remembering that the tau is conjugate linear, you'll get this equation for the functions, right? The GG bar imposed with tau is 1. And then we have to worry about whether or not the tau hat might be isomorphic to the original tau, and so you end up with an equation like this for two functions, f and g, right? And so you can go away and show easily that if m is simply connected, then you can always solve this equation. So what we deduce is that if m is simply connected, then your bundle may, if it has a real structure, it only has one. Well, there aren't any others, up to the obvious isomorphisms. Right, so you can use this kind of argument to see how, on a real space, if you've got your real structure and you know what your bundles are and everything's reasonably simple, then you can work out which ones are real bundles, which ones admit a real structure. Right, so let's have a look at the two spheres. So there everything's simple, right? So the bundles are classified by the Chern class, which is an integer. There's one for every integer. And so remember that if I, sorry, I've overused the word degree here, I didn't mean that. Take out that. So the Chern class of the pullback of P by tau is the degree of the map tau times the Chern class of P, right? And tau's a diffeomorphism because tau squared is 1, and so the degree of tau is plus or minus 1. Either it's homotopic to the identity map or it's homotopic to the antipodal map. Right. They're the only possibilities. And so in those 4 cases I gave you, A and B, right? A was the identity map, and B was the rotation, so it's homotopic to the identity map. The other 2 were homotopic to the degree minus 1. Oops. Let's come back here for a minute. Right, so if it's, in this case where tau is homotopic to the identity map, then tau inverse of P and P have the same Chern class, so they must be isomorphic. But on the other hand, if we're going to have a real structure, tau inverse of P should be isomorphic to the dual of P. So P should be isomorphic to the dual of P. So you can only get that if the Chern class is 0 or P is trivial. So for the real structure for any real structure homotopic to the identity map, you only have real structures on the trivial bundle. So in that case, that's the sort of necessary condition. That's also, yeah, that's just what happens. Right, so for the other 2, you can do the same sort of argument, but it's not quite enough to tell you what happens. So imagine tau is the antipodal map, and we think about the 2-sphere as CP1, complex projective space, right? Then what tau does to a complex projective line with homogeneous coordinates Z0 and Z1 is to flip it to Z1 bar minus Z0 bar. So if you think about the Hopf bundle, depending on your point of view, it's either the bundle with Chern class 1 or minus 1. Then the fibre at the point Z0, Z1 are just all the things, all the multiples of Z0, Z1. So all the W0, W1, I guess I want a principal bundle, so unit length and multiples of this. So so there's a sort of obvious antilinear map I can do, which is a lift of tau. Right? I can, sorry. Well, we can lift tau to an antilinear map by just making this map act in the obvious way on W. W0, W1 does what tau does, W1 bar minus W0 bar. But of course, if you do this twice, you do this again, and you unfortunately pull out a minus 1. Right? So the W1 bar and W0 bar go back to W0, W1, but there's an overall minus 1. So tau squared is minus 1. Right? You think, well, you know, can I multiply tau by something and fix this up? And the answer is no, if you muck about a bit. This can't be done. So the Hopf bundle doesn't have a real structure. On the other hand, if you took the Hopf bundle and you raised it to some even power, and you just raised this map to this antilinear map to the same power, if it's an even power, the minus 1 would go away. So all the bundles with even Chern class have real structures, all the others don't. Right. And on the other hand, the other thing was the reflection, right? The reflection in the equator. This looks like just conjugation on CP1. Right. So now there's an obvious map that you'd send tau of W0, W1 to W0 bar, W1 bar, do it again, you get back to the identity. So that certainly has a real structure. So the situation is if you look at real bundles on the 2-sphere, then if your involution is degree plus 1, only the trivial bundle has a real structure. In the other case, if your involution is got degree minus 1, then the even Chern class ones have a real structure if it's equivalent to the antipodal map. Otherwise, all of them do. Right. So it's an example of the fact that sufficient condition, you know, in case C, you satisfy that sufficient condition that the pullback of the bundle is the dual of the bundle, but it's not enough to get your real structure. So things are just that little bit more complicated than just being able to nail it by knowing how the pullback behaves. Right. So.
Can I just ask?
Yeah, sure.
If you kind of pull that case pseudo-real, would that kind of give you?
Yeah. Or
have a theorem?
Or call it quaternionic. Yeah.
Is that the only obstruction? Is that the only problem?
That's the only problem for this example. Yeah. Yeah. Right, so to get further, I want to introduce a cohomology theory that I don't really want to say very much about except what the groups are geometrically. So this comes from the Hoko paper where he introduces a cohomology for sheaves with group action. So we've got a sheaf with a group action as a very simple group, but Z2. So there's a number of bits of notation we need. So U1 I'm going to use for the sheaf of functions with values in U1. And I'm going to use the same thing again for the sheaf with the group action where Z2 acts trivially. I'm going to use it with a bar to mean the sheaf with the group action where Z2 acts by, with a non-trivial element acts by conjugation on the sheaf. Right? So in such a case, you can go away and work out these various cohomology groups by a spectral sequence. And so simple sort of examples are, so H0 of mz2 u1 bar are functions which satisfy this condition. Remember I said these were real. H0 of mz2 u1 are functions that are fixed by the action of tau. U1 bar, the H1 are bundles with a real structure. U1, they're bundles with Z2 structure. And so there's a good way of putting these all together into a long exact sequence that's helpful for calculating these things. So remember also that, of course, H0 M U1 are functions from M to U1. H1 M U1 are U1 bundles, so they're in there as well. And so there's this exact sequence. Luckily, I have colleagues who know how to use XY pick something. So let me explain what this is geometrically. It's the simplest way to understand it. Right. So here we've got real functions, and then we think of them as just sitting inside U1 functions, forgetting about the fact that they're real. If I take any U1 function and I multiply it by itself composed with tau, then I get something which is fixed by tau, of course, right? If I compose this with tau, I get itself again. So that's a map into things that are invariant under the Z2 action. And then if I take real bundles, I could forget they're real bundles and get U1 bundles. If I take U1 bundles, I could do the same sort of trick as here, right? This is really secretly the pullback of G by tau. So I could form P tensor product tau inverse of P, and then this would have a natural action of tau on it, right? Because if I pull it back by tau, there's a canonical identification with itself just by flipping the tensor product, right? And then, right, so this is where we're heading, the real bundle gerbes. Here, this is H2 of MU1, which we know are bundle gerbes, and so we really want to understand these two things. And then we can work out actually geometrically what the connecting homomorphisms are, so how to turn a Z2 equivariant bundle into a real bundle gerbe. But I won't have time to say too much about that. Right, so I now need a sort of slight digression into bundle gerbes. So let me remind you about a whole lot of useful facts about U1 bundles. Some of the useful facts, there's about another slide's worth I'm not going to do. But so if I take a U1 bundle, then it satisfies all the following things. I can tensor two of them together. I can take the dual, best to think of them as Hermitian line bundles, but it doesn't matter, you can do it on the group level. If I have a U1 bundle, I can pull it back, U1 bundle over M, they pull back. They're all determined by their Chern class, and the Chern class satisfies these sort of multiplicative properties. It's natural under pullback, it's multiplicative for tensor products, it changes sign under duals. A bundle's trivial, so it's a product if and only if the Chern class is 0, and a trivialization amounts to an isomorphism from P to a trivial thing, or in fact a section of P, and they differ by functions. All right, so the simple answer to the question of what is a bundle gerbe is that it's exactly the same thing. Well, no, not exactly the same thing. You invent some object that does all these things, except that 2 should be a 3. And this bit down here gets a little messier, and you call this something else. But yeah, it's some object which is essentially sort of abelian. You multiply it together, there are duals, there are pullbacks. It's got a characteristic class in H3. Right, so let me just say something about the exact definition, because I've probably got time. So we need a surjective submersion. And so the reason we need surjective submersions is because if we could take vibrations. Vibrations are nice things. Surjective submersions have the property that in the category of manifolds they pull back, right? So you have a subjective submersion, you pull back, it's a surjective submersion. But vibrations, you know, would be movement more pleasant. But there are examples where you need a surjective submersion, you don't have a vibration. So you have to have surjective submersions. And if you have such a thing, you can form the fibre product. So these YPs, the p-fold fibre product of a surjective submersion, is itself a surjective submersion because you're pulling it. I mean, the fibre products are really pullbacks to the fibre product of one lower amount. Right, so bundle gerbe then is a pair. So you've got a manifold M, it's a bundle gerbe over M, but it's a pair of things consisting of well, as an easy answer, it's a, you know, when you've got a surjective submersion, that if you take the fibre product of Y with itself, you get a groupoid, and if you like the groupoid language, then a bundle gerbe is a U1 extension of groupoids. So the definition really just I'm about to give you spells that out. So this fibre product has two maps going down to Y. Y has some projection down to M, and we want a U1 bundle over here. Right, so that's all the structure, and then there's a multiplication, which is, you know, the groupoid multiplication really. So if I take Y1 and Y2 over here in Y2, and I look at the fibre of P there, and I look at the fibre of P over Y2, Y3. So Y1, Y2, Y2, and Y3 are composable in the groupoid structure on. Right. So I want to lift that, and so I want a multiplication like that. And right, and I want it to be associative, right? So there's some diagram you can draw, which is essentially just saying that this is an associative multiplication. If I take three things in here, I could first multiply those two and get into there, and then down to there, or I can multiply the second two and get across to there. So I want this to be associative, and then that's everything you need. Okay, so I have that list of properties, right, of what bundle gerbes should satisfy. So let me just sort of sketch why a couple of them are true. So products, right? So if I've got two bundle gerbes, Py and Qx, so y and x are submersions, so I could form a surjective submersion, which is the fibre product of y and x, and I can write down a bundle over, I can write down a bundle over there by defining its fibre at y1, x1, y2, x2. That's 2 points in here. That's a single point in here. In this way, so I take the y1 and the y2, so P is a bundle at y1, y2, tensor qx1, x2. So this pair, and then you can work out there's a product, the obvious sort of product. This is the tensor product of these two bundle gerbes. Dual is easy, you just take the dual of P. Pull back straightforward because you could pull back y and get a new surjective submersion, then pull back P over y squared. And so there's a more complicated thing you've got to do, which is find the characteristic class. And so there's a thing called the Dixmuir-Doherty class for a bundle gerbe, which is a class in H3 of MZ. And I won't define that. There's a reasonably simple check definition. Right, so then it satisfies the kind of things that you would expect. Right, so the complication is that with bundle gerbes is that unlike bundles where Chern class 0 means the bundle's trivial, Dixmuir-Doherty class 0 means the bundle's trivial, but there are lots of the bundle gerbe's trivial, but there are lots of trivial bundle gerbes, right? I mean, you might think that the trivial bundle gerbe was something like take the simplest possible surjective submersion you could think of, take the fibre product of that, which is 2 copper. that again, yeah, right. I knew it was simple. And then take that, right? So that would be sort of the most ultimately trivial bundle gerbe, but there are a lot more than that, right? And so what there are, I mean, essentially, triviality is like sort of a category equivalence thing. So there are lots of things, the object space can vary a lot. Right, so what you do is pick a U1 bundle over Y. So this is how you characterize all the ones that have zero churn class, Dixit-Medjuity class. So pick a U1 bundle over Y, and then you can form a U1 bundle over Y squared by doing this. So delta Y, it's called delta R. No, it's not. It's called delta R. So delta R of Y1, Y2 is RY2 tensor RY1. So now if I look at so if I try and write down a multiplication, I want to look at something in here. So that's going to be R, which way did I do it? RY2 tensor RY1 star tensor RY3 tensor RY2 star. Right, and I can sort of contract these two things, and I end up in RY1 star tensor RY3, which is delta R of, yeah, Y1, Y3. I'm taking a check that that's associative. Right, so something like this is called trivial, and you can go away and calculate. Had I told you what the Dixit-Medjuity class was and how to calculate it, it's not hard to calculate that such a thing has zero Dixit-Medjuity class, and they're the only ones. Right, so the bundle gerbe is called trivial if it's isomorphic to such a thing, and such a choice of thing and the isomorphism are called a trivialization. Right, it's got zero Dixit-Medjuity class if it's trivial. Right, so remember that if you take U1 bundles, then a map from P to Q can be thought of as a section of P star tensor Q. Right? And as a section, it's a trivialization. So you can sort of turn this on its head and say that, you know, maps from P to Q are trivializations. So let's invent the idea that a map from the bundle gerbe G to the bundle gerbe H should be a trivialization of G star tensor H. Right, and so we call this stable isomorphism, just to not mix it up with isomorphism. And a choice of such a trivialization is called a stable isomorphism. And in fact, these things are morphisms. They're composable, right? If I've got a trivialization of G star tensor H and a trivialization of H star tensor K, I can in fact compose them and get a trivialization of G star tensor K. It's not as obvious as the sort of contraction makes you think, as the way the notation makes you think, but it does work. And then stable isomorphism gives you an equivalence relation, and the equivalence classes are exactly what H2 of MU1, H3 of MZ's classified. Okay, so let me just make one comment about the sort of hierarchy of things here. So there's a sort of hierarchy of objects starting out with functions, U1 bundles, bundle gerbes, bundle 2 gerbes, which of course goes on and becomes like all these higher category things more complicated. And so in some vaguely silly way, functions into U1 could be called -1 gerbes. But I don't think this is going to catch on. So another comment, given the fact there's a C-star algebraist in the audience, so lots of people know that continuous trace C-star algebra has something called a Dixit-Medjuity class. And so this construction that we saw this morning for the Fell bundles, if you do the sort of trivial case of that, right, where the bundle is a U1 bundle, then there's this construction that lets you get from a bundle gerbe, essentially, to a C-star algebra, except you would need the Y to have a Haar measure, right, to do this. And most of the Ys that turn up in examples don't have sort of Haar measures because the fibers of Y want to be infinite dimensional. If the fibers of Y are not. So if the fibers of Y are finite dimensional and connected, the Hekmati class is torsion. So there's an analogy between, yeah, so this is a correspondence with C-star algebras, but for a lot of bundle gerbes, you can't, there isn't a C-star algebra. Right, so I wanted to just do one example. So, with bundle gerbes, you might ask, you know, where do I expect to find them? And obviously, you expect to find them whenever you've got an integral, you've got a manifold with a 3 class. And so, for example, there should be a bundle gerbe over compact, simply connected Lie group. So, for example, for SUN, and then with such a case, there's this. Well, this is a general. So this is a general construction of a bundle gerbe, given that I've got an integral 3 form representing some cohomology class. And so what you do is you need a Y, right? So you've got an M and you need a Y, and so we take Y to be the path space of M for some paths based at some point. Right? And we take the projection to be the map, the other endpoint map. Right, so we evaluate at the other end and project down to M. Right, and so then we form Y squared. And what we find is that, of course, Y squared are all the things that start here and agree somewhere else. Right. And I want to attach to this, to such a pair, the fibre of some U1 bundle, and so this is how you do it. It's the construction of a line bundle given a 2 form essentially. But right, so I'm going to assume this is 2 connected, so I can close this thing off with some spanning surface, say sigma, and so then I've got things like, let's call that gamma 1 and gamma 2. I've got a gamma 1, gamma 2, sigma, and a Z. And did I put all those in that notation? Oh, sorry, my paths were P. P1, P2. Right. And I want to write down the equivalence relation, and after I form the quotient, it's going to be a U1 bundle. So this will be equivalent to some other thing if I, right, so I pick another surface, sigma 2, so you've got 2 surfaces with boundary P1 and P2, and so it's 2 connected, so you can fill that in with a ball. The boundary of the ball is sigma 1 union sigma 2, and we put on this equivalence relation, right? Oops. Right, so those of you know what the Wess-Zumino-Witten term is, this is the Wess-Zumino-Witten term for this, as in Wess-Zumino-Witten sort of field theories. Right. And so, of course, there's lots of choices here, mainly particularly the choice of the 3 manifold B. If you take a different B, then the 2 B's have common boundary, sigma union sigma dashed, and so you can take the union, and then you find that this H is meant to be an integral form, so when you integrate over B union B dashed, you get an integer, and so this doesn't make any difference. All right, so that's a construction, and then there's a multiplication map, right, which you can sort of work out. All right. Okay, so what's a real bundle gerbe? So you make the involution act on everything in sight. Right, so this idea is in thesis of Mutu in a slightly more complicated bundle gerbes with a grading. I don't want to do. Right, so given that you've got M, you require that M lift to a map between Y, and therefore automatically, you can lift it to the fibre products, and then you require that it lift to P and be anti-linear. Right, so you've got a surplus of taus at this point. They could be called tau sub y, tau sub y squared, tau sub p. Oops, sorry. By the end of the lecture, I'll remember which button's which. Right, so given the bundle gerbe, you lift it to a tau sub y, and then you lift that to a tau sub p. And this, again, when you get to the bundle level, it's got to be a conjugate involution and commuting with the bundle gerbe multiplication. Right, so then it's a real bundle gerbe, and the existence of these tau sub y and tau sub p are called a real structure. Right, so you can check that it sort of behaves in the obvious way. It commutes with pullback, products, duals, and things like that. So the only other thing is, what about trivialization? So that's not too hard. So what you do is, with your auxiliary sort of bundle R over Y, you ask that it have a real structure, and then that the real structure on delta, so that induces a real structure on delta R, and you require that be the same as the one on P, and in that case you call it a real trivialization. Right, so then it turns out that what you might hope to be true is true. Bundle gerbes are classified up to the real stable isomorphism by their something you can construct called the real disambiguity class living in this space. Right, so then you can go back and identify some other things in this sequence. Right, so this gives you a handle on trying to construct real bundle gerbes. You could look at Z2 bundles and try and work out what this connecting homomorphism means geometrically. And then, of course, you could go on to bundle 2 gerbes, which are somewhere around the back here. Right, so one interesting case is that this cohomology doesn't have the property that, cohomology of point is trivial. So if we put a point in everywhere here, so here we'd be looking at, so everything else would just vanish, right? This is bundles over a point, that's 0. Right, so this would be bundles over a point with a Z2 action. Right, so the only thing you can really do is act on the fibre. But there are two things you can do. You can just act, or you can act by the identity or by -1. So there are 2 Z2 bundles over a point up to isomorphism. It turns out. All right, and so therefore there must be, right, so bundle gerbes, there won't be any bundle gerbes over a point because they're classified by H3 of MZ. And so there must be, up to stable isomorphism, real stable isomorphism, there must be 2 real bundle gerbes over a point. Which seems like a slightly bizarre fact, but nevertheless is true. Right, the other thing you can do is worry about how you would construct these things. And so one case that helps is if you had if your real structure on M's got a fixed point, then you could come and look at this construction over here, and you would see that a really good thing to do would be to make this base point a fixed point. Right, so then when I apply tau to a curve, it at least begins in the same place, right? And so I would have a map to y covering tau. Right, and you can go through, and so if you have some other conditions, such as this H being mapped to minus itself, right, right, so you want tau to pull back the 3 form to its negative, and then you look at this construction and you'll see that you can define real structures everywhere. So one such case would be if you take the group SUN and you take the inversion, right? And so then the usual form is some multiple of G inverse to G cubed, and so it goes to its negative. Right, so on the 3 sphere, that of course looks like right, so it's got fixed points up here at 1 and another fixed point down here. If this is SU2, and otherwise it's the antipodal map on all these equatorial 2 spheres. So this is such a case, you can look at paths based at the identity and do this construction. Right, so maybe I won't go through that. It's sort of, you have to absorb the construction and then you can see that it's sort of obvious. Everything behaves in the way you want. The minus sign does exactly what you want it to. This minus sign is ultimately going to be the cause of getting a P star rather than a P. You want a P star. Right, so Yandel gerbes. So, as I said at the beginning, the way I've done the real structures is they're kind of like a strong real structure in some sense. You know, that all the lift of tau, all the things are isomorphisms from y to y, and they're not stable isomorphisms. If instead you tried to use stable isomorphisms, you would recover really what's the definition. In some ways that's the natural thing to do. But you recover the definition of what we looked at earlier by Schreiber and Schweigart and Waldorf, and called Yandel gerbes. So a real bundle gerbe, because isomorphisms actually give you stable isomorphisms, a real bundle gerbe is a Yandel bundle gerbe. A Yandel bundle gerbe doesn't have to be a real bundle gerbe. And so you can go through and just do all the same things, right? You can get a Dix-Medjugorje class of a Yandel gerbe. They're classified by the same space, and so the space of Yandel bundle gerbes up to sort of Yandel stable isomorphism is the same as the space of real bundle gerbes up to real isomorphism. However, there's a sort of annoying feature of this, so let me have a sort of short mathematical whinge about equivalence relations, I guess. I'm interested in sort of finding out whether things have a real structure, and all these results, even though they're useful, they tell you things really about whether or not. So here you've got a bundle gerbe, and maybe you know that topologically the bundle gerbe, right, so maybe I know I've got a bundle gerbe in here, and I know it comes from this space over here. Well, I better do it at the level of cohomology, I guess. But yeah, so I know about the cohomology. I know it's Dix-Medjugorje class. For some reason I can see that it's coming from the real Dix-Medjugorje class of something. And I would like to then know that I could confidently go looking for a real structure on the bundle gerbe, and I don't, right? All I know is that I can confidently look for a real structure on some other stably isomorphic bundle gerbe. And stable isomorphism is a really weak sort of equivalence relation. It doesn't mean that there's going to be a map on the y that I've got in front of me, which I might have some nice geometric realization of. So that's just an irritation. Whereas, you know, if you went back to bundles and you have a bundle, you want to get a real structure on it, either you can or you can't. You know, it's not living on some other unrelated bundle. So, for example, Danny and I have this construction we like that Ulrich was mentioning earlier about the basic bundle gerbe on SUN. And so I know from this construction that the basic bundle gerbe on SUN has a real structure. But there's this other construction, and I can't prove that it's got a real structure. In fact, I keep getting something with j squared equal to minus, tau squared equal to minus 1, which scares me a little bit, but I don't know what's causing that. So one final calculation, which I'm just going to tell you the answer to. So let's look at the circle cross the 2 sphere, take the real structure, which is the antipodal map on the circle and the identity map on the sphere. And then I claim that long exact sequence sort of collapses down to this. And so this tells you that, right, so these are U1 bundles on S1 cross S2, which are determined, of course, by the Chern class and the S2 factor. These apparently are U1 bundles with an action of Z2. These are bundle gerbes on S1 cross S2, determined by the H3 of this. And this is the space of real bundle gerbes. And so these are the maps. So this is the basic, the sort of standard bundle gerbe with interclass. Yeah. And so as you make the spaces more complicated, these things get sort of rapidly quite complicated. Right, so they're the references in case you're wondering. All right, thank you.
Anyone have any questions?
Suppose you take a suitable, I guess, real bundle gerbe, similar conditions to what you had for making the continuous field C-star algebra.
Yeah, yeah.
And do you then get a C-star algebra with an involution, what somebody, I guess, Casparo called a capital real C-star algebra?
Yeah, you should get, yeah, I've talked to Jonathan Rosenberg about this and he insists that, yes, it'll work. I haven't done it myself, but yeah. Yeah, you should get a real C-star algebra.
And if you take a continuous trace C-star algebra, say locally trivial, but not necessarily torsion, DCA to a D class, can you still actually manage to get it from some suitably chosen?
Yes, yes, you can always take the, yeah, so. This goes back to this paper by Rayburn and Taylor, a long time ago. Given M and a 3 class, you can always take an open cover.
Yes.
And represent it, and say make the Y the disjoint union of the.
Oh, I see. Okay.
Right. So then it's a surjective submersion, but the fibers are wholly disconnected.
Yeah.
There's no problem. There's no the sort of non-existence theorem doesn't apply here. Yeah.
Well, if there are no further questions, let's thank the speaker again.